Hello. It is April 9th, 2020. Oh, what? No, it's April 8th. Sorry, 2020. Well, this is a Calculus 2 lecture. Today we're going to be talking about geometric series, divergence test, and harmonic series. I hope to get through these three topics. Couple things just to review. We have we introduced yesterday the idea of infinite series here, which really you should think of as being a limit of a certain sequence, and that's the sequence of what we call partial sums. So on the one hand, one way to think about infinite series is as the sum of infinitely many numbers. So we have A1, A2, A3, and it's like we're adding all of those numbers up. So that's one perspective that you can take on infinite series. But the sort of, I would say, more rigorous way to think about what an infinite series is that, okay, so we associate to this sequence of we associate to the series here a sequence of terms, A1 through A blah, AN, and then we have the sequence of partial sums, which is a different sequence. We give that the name S. S1 is just A1, S2 is A1 plus A2, S3 is the sum of the first three terms, Sk is the sum of the first k terms of this infinite series. Okay, so we can compactly write that in this way using sigma notation. And what we mean when we talk about the sum from n equals 1 to infinity of a sub n, what we mean by that is down here. We take the limit as k goes to infinity of the sequence of partial sums. This is a limit of a sequence. So this is a topic that we talked about in the lecture prior and perhaps the lecture prior even before that. Okay? And we had certain adjectives that we would attach to a sequence. We would say that sometimes a sequence was convergent and sometimes a sequence was divergent. And so that is how we define the notion of convergence and divergence for infinite series. Okay? We say that this infinite series here is convergent if the limit of the sequence of partial sums is a convergent sequence. And we say that this is a divergent infinite series if the limit of the sequence of partial sums is divergent, doesn't exist. Right? Does that make sense? I don't know. There's nobody out there to tell me whether that makes sense or not. If you could type in the Twitch chat and just let me know if what I'm saying makes sense, that would be very helpful, because that just sometimes feels like I'm talking into the void, which is less helpful. Anyway, a very important family of series that we can talk about are geometric series. Geometric series here are defined in this way. It's the sum from n equals 0 to infinity of a r to the nth power, right? Which looks like this. A plus AR plus AR squared, etc. And then the key thing about geometric series, there's only ever two parameters that you need to care about with geometric series, namely A and R. They are then assembled in this manner for you. And the relationship, the key thing about a geometric series is that if you look at the ratio of subsequent terms, so look at A and AR, the ratio of AR to A is R. But notice this, that also holds for the next two terms. If you look at these two terms right here, AR squared and AR, the ratio of AR squared to AR is also R. So the thing, I guess, which characterizes geometric series, if we wanted to use a word, is that the ratio of subsequent terms in a geometric series is always equal to some number, some fixed number, which we call R. Okay? So in this example here, we have a geometric series where A is 1 and R is 1/2. A equaling 1 means that the first term of the geometric series is 1. See? There's A right there. And here's A for this particular example, namely 1. And R is 1/2, so what we do is to obtain the next, if we didn't know, to obtain the next term in the sequence of terms of this geometric series, what we do is we take that 1 and we multiply it by 1/2. And that gives us, of course, 1/2. Then we take that 1/2 and we multiply it to get the next term. We multiply it by 1/2 again, which is 1/4, and we keep going in that manner. Is that clear? Yeah, so that's what this infinite series here is. Here's another example of a geometric series down here. Now, looking at these sigma notations, you can see that they're very similar looking, except that down here we're starting the index n. Instead of starting it at 0, we are starting it at 3. And that does have a material effect. What that does is that changes the value of a. A is always the first term of a geometric series. R is always the ratio of subsequent terms in a geometric series. And so you can see that. Right? All right, here we had my geometric argument for why this series here, I didn't even write the conclusion, this series here is equal to 1. That is to say, we have an infinite set of numbers here that we're adding up, and magically somehow they all add up to 1. And I mean, you can kind of do this with your calculator if you really want to. What you can do is add up these infinitely many numbers by just plugging it, putting in your calculator 1/2 plus 1/4, and then you can add to that 1/8 plus, and then press the plus button 1/16. And what you'll find is that these numbers get closer and closer and closer to 1. But here is a geometric argument that I've supplied to you of that. One could also, it occurs to me, make a computer script which can do this. Maybe if I have time and I remember to do that, I can do that here today in this lecture, since I have a computer, very capable computer right in front of me. Okay, now remember that in general, when you're looking at a infinite series like this, any infinite series, but this happens to be the general form of a geometric series. When you're looking at such a thing, okay, what you're really thinking about is this limit of the sequence of partial sums. Okay, so in asking the question, when does a geometric series like this converge or diverge, what we are particularly interested in is figuring out what the sequence of partial sums for this geometric series here looks like. And that's the argument that I give here. What I do is I start with this infinite series, and I write down some of the partial sums. I do this just for pedagogical purposes, right? These are the first 3 partial sums of this infinite series. This is the sum of the first term. This is the sum of the first 2 terms. This is the sum of the first 3 terms, I guess. And it's a little bit weird because the index starts at 0, so it's a little bit confusing. But I don't know, just deal with it. Here's S sub k in general. All right, it's got k plus 1 terms in it. It starts at a and it ends up at a to the r, a times r to the k power. Here's r times S sub k. Now you might be wondering, why in the world would I want to think about that quantity? Well, I do, and I get that here. And the magical thing is to notice is that S sub k and r times S sub k share many, many terms in common. So if I do the subtraction here, we get massive die-off in the terms which cancel each other. And the only terms which survive this massive culling is this first term a, and this very last term a to the r to the k plus 1 power. Okay, but this term here gets a minus sign. So we get this equation. If I subtract from S sub k, r times S sub k, we have a minus r to the k plus 1. What I can then do is factor out the S sub k from the left-hand side, because you notice that it's a common factor on each side. So I can factor it out, and what I'm left with is S sub k times 1 minus r. And then I can divide both sides by 1 minus r. Is that clear? Now, you might be objecting if you're really nitpicky. So the question was asked, where does the minus come from? So remember, I'm subtracting r times S sub k from S sub k. That's what I'm doing here. So where does the minus come from? It comes from right there, from that minus right there. Okay? Hopefully that's clear. Sorry, so let me back up. You might be objecting in this formula well, am I really allowed to divide by 1 minus r? Is that really a legit thing that I can do? And the answer is yes, as long as, of course, 1 minus r is not 0. Because if 1 minus r is 0, then this is no longer legit. Yeah? So I guess I should have said that. It didn't occur to me to say that yesterday, I guess. I was in a bit of a hurry when I explained this yesterday. So here I'll just say r cannot be 1 for this formula. Obviously, because if r is 1, then we're dividing by 0. That's no good. All right. So that was yesterday. What about today? Well, let me get a clean sheet of paper here to work from. What about today? So I want to keep talking about geometric series because I want to give you a really complete answer as to when they converge and when they diverge. Focus for me. So we're going to work from that thing. So more on geometric series. So what these are is the sum from n equals 0 to infinity of a times r to the nth power. Did I write this right? Yeah. And what we learned yesterday, and the thing that I'm going to just assume, is that the sequence of partial sums, S sub k, has a kth term, okay, which is given by this formula that I gave you yesterday, which is a minus r to the k plus 1 power divided by 1 minus r. And this is true as long as r is not 1. By the way, we can think about what S sub k looks like if r is equal to 1, right? If r is equal to 1, notice that this sum is the sum from n equals 0 to infinity of just a, okay? And so what is the sequence of partial sums going to look like? Well, S sub 0 will just be a. S sub 1 will be a plus a. Oh, yes, sorry. Thank you. I goofed a little bit. I forgot the a here. S sub 2 will be, S sub 1 will be a plus a. S sub 2 will be a plus a, etc. And so you can probably work out what the kth partial sum looks like in that case. Cool. So let's start here. Now remember what we mean by this infinite series. It's a limit of the sequence of partial sums. So this is the same thing as the limit as k goes to infinity of S sub k, which is, of course, by what we just said, the limit as k goes to infinity of a minus a r to the k plus 1 power divided by 1 minus r. Okay? So we should think about what's happening here. Well, what I claim is the following. What I claim is that, let's see. Where is k in this expression? K is in the power of this r. And as k goes to infinity, we can all agree that k plus 1 also goes to infinity. That's clear, right? K is getting larger and larger and larger without bound, and so does, therefore, k plus 1, right? So, and that's the only place where k plays a role in this expression. So in analyzing this limit of the sequence of partial sums, really all we're thinking about is what's happening to this guy right here. That's the only thing that's sort of changing, or changing as k gets larger and larger and larger. The question is then, how does it change? And I hope that it's plausible, I guess, that that's going to really depend on what r is, right? Like, let's say r was 2, some number like 2. Can we imagine? Let's suppose r was 2. Then, as we raise the power on that 2, as it gets larger and larger and larger, we have something like 2 to some power, and the power is growing, right? So we have like 2 to the 5th, 2 to the 10th, 2 to the 100th, 2 to the 1000th, and what you should understand is that those are bigger and bigger and bigger numbers. So if r is bigger than, and that's going to be true anytime r is bigger than 1, if r is bigger than 1 here, this term in this box here is going to go to infinity. Is that clear? However, if r is less than 1, let's say r is between 0 and 1. If r is between 0 and 1, then as we take higher and higher powers of r, those numbers are going to shrink in value. They're going to get smaller and smaller. Like imagine that r was 1/2. 1/2 to the first power is 1/2. 1/2 to the second power is a smaller number, namely 1/4. 1/2 to the third is yet a smaller number again, namely 1/8, etc. And these numbers get smaller and smaller and smaller. They go to 0. Okay? So here's the complete answer to what the value of this limit here is. This is equal to one of two things. Okay? I'll say it like this. This is equal to, so what happens as k goes to infinity is, again, if r is less than 1, between 0 and 1, this thing will die. But it actually also happens for when r is negative, but between 0 and 1 in absolute value. So I'm just going to write down the answer. It's a over 1 minus r if the absolute value of r is less than 1. And it's divergent otherwise. Or let me say it like this. Does not exist otherwise. Now, what I mean by does not exist, it could include the situation where this limit blows up to positive infinity. For example, if r is 2, then this thing blows up to positive infinity, right? Yeah, but this is what I'm saying, is if r is less than 1 in absolute value, then this term here inside this red box goes to 0. And what we are left with is a over 1 minus r. Okay, so maybe I should write that down. So this box here, just for this box, this thing goes to 0 if the absolute value of r is less than 1, and it blows up if the absolute value of r is greater than or equal to 1. I guess it doesn't blow up if it's equal to 1. If it's 1, then it just is always 1, 1, 1, 1, 1. But if it's ever even a smidge bigger than 1, then what you'll find is that thing blows up. Okay? All right. So what that suggests, okay, about geometric series. So this is, I guess, the really important takeaway. The sum from n equals 0 to infinity of a r to the nth power, this thing, we can say, converges. And not only can we say that it converges to a certain value, namely a over 1 minus r, if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than or equal to 1. Okay? This summarizes basically so much, almost everything that you need to know about geometric series is in this box right here. This is a very good summary. Okay, so let's look back at that example I did of the square that involved the geometric argument, namely that square thing. So example, we had the sum from n equals 0 to infinity of 1/2 to the nth power. And I claimed, and I was right, that this is a geometric series. This is equal to 1 plus 1/2. Oh, I guess I started there. I guess I started in that problem. Let me just look. Yeah, I started the index at 1 instead of starting it at 0. It's still a geometric series, okay? But I started it at 1. And so, in fact, the first term was not 1. It was, in fact, 1/2. 1/2 plus 1/4 plus 1/8 plus ... And what we said here is that a was equal to 1/2, and we can see that because it's right there in front of our face. And r, the ratio of subsequent terms, was 1/2. So now let's apply this box to this geometric series. What can we say about this geometric series? Well, because r is 1/2, that means that it's less than 1 in absolute value, right? And so that means that it converges. This geometric series converges because the absolute value of r, which is equal to the absolute value of 1/2, right? R is 1/2, which is equal to 1/2, is less than 1. And not only can we say that it converges, but we can say what it converges to. It converges to a over 1 minus r, which in this case is 1/2 upstairs divided by 1 minus 1/2, but 1 minus 1/2 is 1/2, and this is clearly 1. Okay, so it's a convergent series, and it converges to 1. So that's kind of special. Is this clear? All right. And I guess maybe one more example what we can do. Let's say that we had a set of parameters like, I don't know. Let's say we have a geometric series with a equal to, I don't know, 5, and r equal to, let's say, negative 1/3. Okay? So we can form such a guy. And if we do, looking back at the general form, what we're saying is that we've got a series, sum, from n equals 0 to infinity, of 5 times negative 1/3 to the nth power. That's our geometric series. And you should be able to tell me whether or not this converges or diverges. That's a relatively easy question, is it not? But further, you should be able to tell me, please, what this thing, if it converges, to what it converges to. Was that English? I don't know. Well, anyway, you should be able to tell me if this converges, what it converges to. Okay, so just take a moment, think about that. If you're watching asynchronously, you can probably figure it out. Just give a second. So this is definitely convergent, okay? This is definitely convergent. This thing converges. And the reason is simple. The absolute value of r here is the absolute value of negative 1/3, right? The absolute value of negative 1/3 is 1/3, and that's less than 1. And as long as r is less than 1, we have a convergent geometric series. So this is convergent. Now let's see what it converges to. Converges to a over 1 minus r. What is a in this case? It's 5. And what's 1 minus r? It's 1 minus negative 1/3. Right? So this is going to be 5 over 4/3, which is the same thing as 15/4. Okay, so we have a geometric series which converges, and it converges to 15/4. Yes, very good. Great. So that's like everything I want to say about geometric series. They're super, relatively speaking, they're a very well understood family of series. We can answer all questions that we have about, that we care about, at least for the purposes of this class, we care about with geometric series, which are basically just convergence and divergence. And not only that, but we are extra lucky with when it comes to geometric series, because when it does converge, we can say what it converges to. This is actually a very rare state of affairs. It's not always the case that this will be the that this will happen for us. Okay. All right. I want to, let's see, it's about halfway through. That's very good timing. Good. I want to break out of this discussion of geometric series and talk a little bit more generally about series. Because, so what is the central question actually for us with this geometric series, with infinite series, the central question that we are going to be interested in is when a series converges and when a series diverges. That's like super important to us for reasons that you will find out later, okay? All of this, by the way, of course, is in the service of trying to understand functions better. All of this is in the service of eventually getting to understand Taylor series, is what I'm getting at. And there, issues of convergence and divergence are extremely important. So, like I said, the primary question that we are going to be interested in with infinite series is when a series converges and when it diverges. And what we want to be able to do is be able to look at a series and determine based on its form whether or not it converges or diverges. Now what we need are a suite of tests. Remember when we were talking about issues of convergence or divergence with improper integrals, we had what we called the limit comparison test, and we also had something called the direct comparison test. These were ways or methods that we could use, that we can employ to determine the convergence or divergence of an improper integral. Well, we're going to develop a similar suite of tests, but this time for infinite series. And the first one I want to give you is very important. It's called the divergence test. The divergence test. And as the name implies or suggests, what it says is that it tells you when certain infinite series converge. Or sorry, I messed up the whole thing. I haven't had any coffee yet. It tells you when certain infinite series diverge. Okay, that's the conclusion that you can draw from the divergence test. That's why it's called the divergence test. So what does it say? So the divergence test, what it says is the following. What does it say? Oh, right. I know what it says. It says that if the limit as n approaches infinity of the sequence of terms a sub n for a given infinite series, and if this is anything other than 0, if this is not 0, okay, then it is necessarily the case that the sum from n equals 0 to infinity of a sub n, or n equals 1, it doesn't really matter, diverges. This is it, the divergence test. This is the first weapon in our arsenal to understand when an infinite series converges or diverges. Okay? This is the divergence test. All right. Well, let's see, how should I proceed? Let's just understand understand how we can use this. So, example. Let's look at the sum, this infinite series, of n over n plus 1. Now, one thing I would like to notice is that this is not geometric. This is not a geometric series. Okay? To prove that to ourselves, let's look at this, the first few terms of this series. So let's begin by plugging in 1. If we plug in 1, we get 1 upstairs and 2 downstairs, so we get 1/2. What's the next term? Well, if we plug in n equal to 2, we get 2 upstairs and 3 downstairs. Plug in 3, we get 3/4, etc. Hopefully you see a pattern and you could write out more terms if you wanted to. But this is what the series looks like. Okay, so if this was geometric, right, then what should be true is that the ratio of subsequent terms should always be equal. So it should be the case that, for example, 2/3 divided by 1/2, which is 4/3, that should be the same as 3/4 divided by 2/3, right? But what is 3/4 divided by 2/3? It's like 9/8. 9/8. 4/3 and 9/8 are not the same, right? And so this is not a geometric series. So I'm just going to sort of I just want to point that out. Not geometric. This is maybe a thought bubble. So unfortunately, we cannot use the techniques that we just developed for geometric series to understanding whether this thing here converges or diverges. But if I really hope that by the end of this class, you will be able to look at this series here and just say really quickly, at a glance, this thing definitely diverges. Absolutely diverges. I mean, it doesn't even meet the basic requirement set out by this divergence test statement. It doesn't, because I don't know about you, I'm at a point in my life, I guess, where I look at this sequence of terms, n over n plus 1, and I just see something which does not converge to 0, right? I see something, as n gets larger and larger and larger, what I'm seeing is something that converges to 1. And that's because my brain almost automatically says, oh, when n is big, that 1 doesn't matter. That 1 right there, do you see the one I'm pointing at right there? That 1 does not matter. When n is large, this quotient, n over n plus 1, it looks like 1. Because it looks like n over n. This 1 doesn't matter when n is large. It looks like n over n. So when n is large, it looks like n over n, which is 1, which in particular is not 0. So the terms are not going to 0. And that means that this must be a divergent series. That thinking is formalized by what I'm asserting is a convergence/divergence test for infinite series called the divergence test. This statement. Okay? So let's employ it. Okay? Let's examine the limit as n approaches infinity of a sub n. What is playing the role of a sub n here? It's this. That's our a sub n. So Aaron asks, does the divergence test we just wrote down only apply to geometric series? No. It applies to all infinite series. Notice, so when I write something down, I try to be super precise about it. I try. Okay? If one of the assumptions of this statement was that this was a geometric series, I would say so. Please, I would say so. No, this is a general infinite series. It could be any infinite series at all. Okay? All right. So let's look at the limit as n approaches infinity of the sequence of terms a sub n. So this is equal to the limit as n approaches infinity of n over n plus 1. And what is this equal to? Well, or how can we evaluate this limit? Well, we talked about a couple of ways of doing it. One way to do it was to factor and cancel. Another way of doing it is L'Hopital's rule. If you convert this to use an interpolating function, right? Either way works. I'll just do the factor and cancel strat because it's super fast. We factor on n from upstairs and an n from downstairs. They kill each other, and what we're left with is 1. But in particular, I don't care that it's 1 particularly. The important thing about 1 is that it's not 0. Somebody asked a question. I don't see how the divergence test is true in all cases. Can't the limit equal some value L, therefore making the sum of a sub n equal to that value L? No. Okay, so the way you should think about it, let's suppose that this limit here was equal to some number L. Let's make that L be 2, so we're very concrete. All right. So imagine you have a sequence for which the limit is n approaches infinity to a sub n. Let's imagine that that's 2. What that's saying is that when n is extremely large, a sub n looks like 2. That's sort of the statement, right? That's sort of what we can deduce. But if when n is large, a sub n looks like 2, then this sum, when n is large, the portion of the sum way deep, way far out in the sum will look like, some numbers, but then the some number plus some number plus some number, but then way deep out, like at a1000, when we start thinking about a sub 1000 plus a sub 1001 plus a sub 1002, those very high index terms will be very, very close to 2. So that tail of that sum will look like 2 plus 2 plus 2 plus 2, or something very close to it. You see what I'm saying? And you'll have infinitely many of those terms, which look like 2 plus 2 plus 2 plus 2 plus 2. Am I making sense there? And so so the sequence of partial sums has to be going up to infinity. This thing has to blow up if, for example, the limit as n approaches infinity of a sub n is anything other than 0. Does that make sense, Claudio? Anyway, you let me know. Anyway, okay, so yeah, we conclude that, returning to this example, that yeah, the sum goes to infinity. Yeah, this is a sum right here, right? We're summing up the sequence of terms a sub n. And if a sub n is getting closer and closer to some non-zero value, then there is no hope that the sum will converge. It must diverge. All right, so good. We have this statement here. This implies, by the divergence test, oh, sorry, I should be putting my arrow here. By the divergence test, I don't even know why I'm doing arrows. By the divergence test, this series diverges. Okay? This series diverges. And so this is how you use the divergence test. This is how you use the divergence test. You use it to conclude that series diverge, that a certain series, a given series, diverges. If you are using the divergence test, you can never write down a conclusion that a series converges. This sentence, by the divergence test, this series converges, is not a sentence that you should ever be writing down. Never. The only conclusion that you can ever draw from the divergence test is that a series diverges. Okay? Divergence test will never demonstrate that something converges. Never. Okay? So if it doesn't diverge, what do we say? Well, if it doesn't diverge, then it converges. It's a binary thing. Either a series converges or it diverges, and there's no in between or third option there. A series converges or diverges. What I'm giving you now is a statement which will allow you to look at a certain family of infinite series and conclude that they diverge. Is that clear? I can't tell if I'm making myself clear or not. So we don't say by the test it converges. We simply only say it converges. No, I see. If you have a convergent series in front of you, okay? If you have a convergent series in front of you, you cannot use the divergence test to justify that it converges. You have to use something else. Now, we are going to collect a large number of those something else's. Okay? A large number. We're going to have like maybe, well, depending on the amount of time we have, we're going to have 5 or 6 of these tests in the future. Okay? So we don't say by the test it converges. We simply only say it converges. No! Okay, good. Aaron, this leads me right into my next point. So the question was, because if that test was not true, doesn't that say that it converges? The answer is no. The answer is no. This is important. Okay, so question. Very important question. Is the converse... So okay, let me back up. I want you to notice that the divergence test is an if-then statement. If, blah, then, blah, blah. It's an if-then statement. Okay? And it's important for your life that you understand the logical structure of an if-then statement. Okay? Here is an if-then statement. What we can always ask about an if-then statement is the converse true? Is the converse of the divergence test true? So what do I mean by that? I always flash back to a memory that I had when I was a 5-year-old kid. I remember walking on a grassy hillside. There was a playground down here, and I was thinking for some reason about squares and rectangles. And I made the following very important realization, which changed my life. Epiphanic moment for me. Okay? It's the following realization. I realized that if you are looking at a square, there is a square, if you are looking at a square, then you're looking at a rectangle. But if you are looking at a rectangle, you are not necessarily looking at a square. So, in terms of if-then statements, this is the state of affairs. If square, then rectangle. The converse of that statement would be if rectangle, then square. But the converse of that statement is false, right? If rectangle, then square? No. Right? But if square, then rectangle, yes. So the divergence test I want you to think of as being if square, then rectangle. That's that's the statement which is the truth. The converse of that statement would be if you have a series which diverges, then it is necessarily the case that the limit as n approaches infinity of the sequence of terms is non-zero. Is that true or is that false? That's my question here. That's my question. And this is very important. The answer to this is false. The answer to this question is no. Emphatically, no. It is not the case that if you have a divergent series, that the limit as n approaches infinity of the sequence of terms is zero. One does not imply the other. And the most important, you don't conquer, Claudio. What you mean is concur. I just want to make sure that you know that. CONCUR is the word you're looking for. The most important counterexample to this question is the harmonic series. It has a beautiful name. It's a beautiful series. Okay. And what is it? So, the harmonic series. The point. This is the most important counterexample. To the converse of the divergence test. So I've got 6 minutes. That's enough time. So what is the harmonic series? This is very famous, very important. Here's the harmonic series. It's the sum from n equals 1 to infinity of 1 over n. That's what it is. Extremely important. And what is that? It's so humble. It's just 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. That's the harmonic series. You go anywhere in the world, in the English-speaking world, and you say, hey, do you like the harmonic series? And if they're a math nerd, they're like, yeah, I like it. It's awesome. Why? Because it's the most important counterexample to the converse of the divergence test. Okay. It is the rectangle, or it is the most famous example of a rectangle which is not a square. All right. So that's the harmonic series. What are the key thing about this? The key thing I want you to notice that the sequence of terms on the one hand goes to 0. So notice two things. The limit as n approaches infinity of 1 over n goes to 0. Hard to disagree, right? As n gets larger and larger, 1 over n, the n down here in the denominator blows up, right? So 1 over n goes to 0. Cool. That's the first thing to notice. The second thing to notice, okay? Or the second thing that I assert, claim, I'll say claim, because I haven't proved this to you by any means. The sum from n equals 1 to infinity of 1 over n diverges. So if you believe these two things, the first one being obvious, I think, and the second one being much less obvious, I think, at this stage in your life. If you believe these two bullet points here simultaneously, then you will agree with me that the harmonic series represents a counterexample to the converse of the divergence test. You with me? It is a series which diverges, but for which the sequence of terms does not go to 0 as n goes to infinity. Okay? So it's a counterexample. So this, to me, is a question that I ask all the time, in various guises, perhaps. Okay? As a true-false question, like let's say on a midterm or something like that, or a final exam. I ask this question all the time because I think it's very important. The harmonic series is the counterexample, is the thing which makes this statement, this converse, false. Okay? All right. Well, why is the harmonic series divergent? Well, I want to give you something of an argument for that. I like this argument very much. I don't... Why? Why is this happening to me? I like this argument very much. And here's what the argument is. So the sum from n equals 1 to infinity of 1 over n. I'm going to write it in a kind of a goofy way. Good. That's correct, ugly girl. The divergence test would not apply. So the first term is 1, right? I think we can all agree. First term is 1. Hey, what's the next term? It's 1/2, right? So I'm going to write that 1/2 right here. Okay? Now, what are the next two terms? The next two terms are 1/2 plus, 1/3 plus 1/4. You agree? Hard to disagree. So I've written the next two terms right there. What are the next four terms? They are 1/5 plus 1/6 plus 1/7 plus 1/8. Hard to disagree. And then I can write the next 8 terms, right? And why not? 1/9 plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16. And you can see I can keep building this pyramid, right, of terms. I've got one here, 2, 4, 8 terms here. You can imagine the next line, which I'm not going to write out, will have 16 terms. The line after that will have 32. So what is happening here? Why am I doing all of this? Well, because I want you to notice something funny about this. So 1/3 plus 1/4. I want us to look at that for a second. Can we all agree that 1/3 is bigger than 1/4? 1/3 is bigger than 1/4, right? So what we can say about this line here is that this is greater than 1/4 plus 1/4, right? 1/3 plus 1/4 is bigger than 1/4 plus 1/4, because if I replace 1/3 by something smaller, right, then obviously the alligator would rather eat the bigger thing. Clear? And what is 1/4 plus 1/4? Well, it's 1/2. We have down here 1/5 plus 1/6 plus 1/7. But is it not the case that each of these three terms here is less than, or what is bigger than 1/8? So is it not the case that this is bigger than 1/8 plus 1/8 plus 1/8 plus 1/8? And isn't that 4/8? And isn't that 1/2? And then look here. Isn't this giving a very similar kind of argument? This is bigger than 1/16, bigger than 1/16, bigger than 1/16, bigger than 1/16, etc. All these 7 terms here are bigger than 1/17. And so this sum of 8 terms right here is bigger than 8/16. But 8/16 is bigger than 1, is equal to 1/2. And so what am I saying here? If we think about the sequence of partial sums here, okay, we see that it must be blowing up, because what we can do is group these things together, group the terms of this infinite series here together in such a way that they add up to quantities which are bigger than 1/2 over and over and over again. I mean, sure, in the next line it's going to require 16 terms to get to something which is bigger than 1/2, but it will happen. And in the next line we'll need 32 to get something bigger than 1/2, but it will happen. And we have infinitely many terms to work with, right? Because this is an infinite series. So it must be the case that in some sense, this series here, whatever its value is, it's bounded below. It is less than 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2, 1/2, etc. But if you add up infinitely many 1/2s, this thing must be therefore, you get something infinite, therefore this series here must be infinite. And so the harmonic series diverges. Does that make sense? I think that's a really awesome argument. I love that so much. Okay, so you bunch together terms in your series which are bounded below by a fixed constant, namely in this case 1/2. And because you can do this infinitely many times, using the infinitely many terms of this infinite series, it must be the case that this infinite series blows up. Goes to infinity, is what I mean when I say blows up. Okay? Well, I can see I'm 3 minutes over time. And so I'll finish it up here and now. But let me see. What I would like to do is give you a problem real fast. What I would like you to show me is that a certain series diverges. And of course, what I would like you to do for your slip, this is for your slip, is to show me, well, one thing, I want you to tell me, what are you confused about, as usual. And 2, I want you to show me that a certain series is divergent. And sure, what we can do is just take this one. I want you to show me the sum from n equals 1 to infinity of n squared over 2n squared plus 1. Well, I want you to show me why this diverges. Okay? Alright, I love you all very much. I'm going to open up the Zoom meeting now for office hours for the next 2 hours. If you have any questions, let me know. I'm also going to try to upload this guy to YouTube. Love you all. I hope you are all staying safe and staying well. Please look at your email today. I completely spaced it. I've been working my ass off on trying to get these midterm 2 procedures done. So please look at your email and read through that document, and let me know if you have any issues at all with what I've got written there. Okay. If you can't make it, if you got life issues which are preventing you from doing this thing, let me know. Okay, I cannot predict that. I cannot know what's going on in your life that are causing you difficulties unless you tell me. Okay. Like I say, I love you very much, and well, let's talk. I'll open up the Zoom meeting now. Bye.